So this is Scott Lowry and I's presentation on modeling the long-term sustainability of natural gas reserves. Go to the next one. There we go. A brief overview of what we're going to talk about today. What's the big deal with natural gas reserves? Well, natural gas is a non-renewable resources, and that comes in a limited supply, meaning that there's a fixed amount available on Earth that we have the ability to access, and specifically in the United States, given territorial boundaries, we only have so much natural gas available to access at some point. Now, the problem is we have a growing population, and our consumption habits are growing as population increases and also as GDP grows. People use more technology that consumes primarily electricity in the case of natural gas. So as people get more wealthy, they buy more smartphones, laptops, appliances in their home, and things like that that consume a lot of electricity and therefore a lot of natural gas. So as those things are growing, it's important to know how long is our supply of natural gas going to last. Now, natural gas is the largest source of electricity generation by a large margin. It produces 38% of all electricity generated in the United States, and then that's enough to power over 144 million homes across the United States for an entire year. So that's a very substantial portion of the electricity generation in the United States. So it's important, if we want to still have that consumption in the future of natural gas as a source for electricity, it's important to understand how long will this resource last us, and how can we make sure it lasts us longer into the future as our consumption needs and our population grows. The EIA, which is the U.S. Energy Information Administration, predicts that 90 years is the longevity of natural gas in the United States, and that's under the assumptions of constant levels of consumption as in 2018. So no growth in consumption, the same level of consumption going into the future. It'll last us 90 years. And that includes both unproven and proven reserves. So a big ballpark estimate, but it does notice that we are coming to a point where we have to address these issues going forward. What are we trying to accomplish? We're trying to predict a time frame at which natural gas reserves will eventually be exhausted. We're also trying to promote or think about alternative solutions to prolong the sustainability of natural gas. Do we have some solutions that can help prolong the longevity of natural gas as a viable source for energy? Also, we're looking into potential positives and negatives of these alternative solutions. Are they good? What's good about them? What's bad about them? And how can we predict those going forward?
The next section we're going to take a look at is model formulation, and there's two elements to model formulation. First, we have the assumptions that we made, and the second thing is going to be defining our variables and parameters. So starting with our assumptions, the natural gas industry is an incredibly complex one with many different factors that influence supply, demand, price, cost of production, etc. So to simplify the industry so we could do analysis with it, we had to make several assumptions to kind of simplify the data a little bit. Our first assumption is that consumption followed an exponential growth curve. When we first started looking at the data, we noticed that consumption seemed to move with growth in population and growth in GDP per capita, which makes sense. If you have more people that have more wealth, they're going to be consuming more goods. There's a pretty strong correlation, about 0.92 between population and consumption. So we thought, however population grows, consumption is likely to follow. Population, we demonstrated to grow exponentially. And because of that, we assumed that consumption continued to grow exponentially, as opposed to the EIA's assumption that consumption stayed constant. Our second assumption is that demand could be simplified. As I said, natural gas is a very complex industry, and demand is one of the most complex parts of it. So we assumed that we could simplify that demand into a simple equation. We used consumption minus net imports, which I'll talk about in just a second, but that's the primary assumption there. Our third assumption was that production could be scaled to match exponentially growing demand. Since demand is modeled off of consumption and consumption is exponential, as we'll demonstrate later, demand grows exponentially as well. Now, what we're trying to model is how production changes with demand and therefore depletes total reserves. But the assumption there is that production can in fact be scaled to meet the long-term levels of demands that exist kind of as we project out 100 and 150 years in the future. The fourth assumption is that consumer behavior remains relatively constant. You could make an argument that as we grow closer to depletion, firms might start producing less than the optimal profitable level because they want to save resources. People might try to consume less. But these changes in behavior are fundamentally unpredictable, and so we did not include them in our model. The fifth assumption is that new technically recoverable reserves are in fact discoverable. Now, natural gas is a non-renewable resource, which means there is a fixed amount in the ground right now, but we are still discovering more of it each and every year, and our access to it is increasing as we increase our technological methods of pulling and extracting that natural gas out of the ground. So there's empirical to suggest that new reserves will continue to be discovered, but we're assuming essentially that that trend is going to continue into the future. So the next slide, we're going to start looking at some of our variables. And the main variable we're dealing with in this model is total reserves. We're attempting to determine the longevity of our total reserves, and thus as reserves change from year to year, they run out as soon as those total reserves drop below zero. So our primary focus is deriving a projection for total reserves. Now, the way we saw total reserves was influenced by two things: new reserved, which replenished the total reserves each year, and production, which depleted it or took those reserves out of the ground. So we discovered, or we outlined a difference equation to project the year-to-year iteration of those total reserves. So total reserves in year t+1 is equal to total year t plus new reserves in year t minus production in year t. And this will allow us to, if we can project new reserves and production, project the future behavior of total reserves. As you can see in the graph there, total reserves do start to increase. We would expect it to be logarithmic since it's not renewable. But with the limited set of data that we had, we couldn't fit it to a purely logarithmic model. We know that eventually it will demonstrate logarithmic behavior because of how non-renewable resources are defined. But for now, we had to use a different approach, hence this different method in projecting new reserves and production to model that. On the next slide, we'll look at new reserves. New reserves are the amount of reserves or technically discoverable reserves that we find each year. So this can mean we either find new deposits that we can access, or we increase our technology to a point where we can actually extract previously unextractable reserves of oil. The way we calculated reserves is just a difference of total reserves in that year minus the leftover reserves after production of the year before. Now, we tried to model that with an exponential or a logarithmic fit, since it would make sense that it would follow kind of a similar trend as total reserves. But there's so much volatility and unpredictability in the data, especially in the second half of that data set, as you can see on the graph, that made it impossible to match any kind of growth function or any kind of growth curve to it. So because before those large oscillations and variations, we have pretty randomly distributed data. As we'll talk about in the analysis section, we just randomly generated those based upon a normal distribution. And again, we'll discuss that in a second. On the next slide is our final variable, production. We actually use demand as a basis to project production, which means we had to come up with some way of determining demand. Now here, the economic logic behind it is relatively simple. Production or supply often meets demand at some kind of equilibrium. If production isn't quite up to demand, then you're going to produce more because there's positive economic profit. If you're producing more than consumption, there's going to be negative economic profit, so you're going to start producing less. This economic mechanism means that we can most likely project production based upon demand, but we also have to come up with a demand function. So we chose to model demand based off of consumption minus net imports. And the reason this is important is because it's the demand for domestically produced natural gas. Obviously, imports are going to take away from the consumption that deals with domestic demand for domestically produced natural gas, because they're buying it from other places, and exports are going to increase that because other consumers in other countries want to buy American produced natural gas. So that's why we model demand based upon that function. As you can see from the graph, it has an exponential growth curve, which makes sense given the fact that it's modeled off of consumption. So with those assumptions and variables in mind, we moved on to our analysis of the actual model, and that moves on to the next section. There are basically 5 fundamental steps in doing this. The first one, as we see on the next slide, is projecting demand. So given our values of demand, so consumption minus net imports that we calculated from the empirical raw data, we were able to fit an exponential growth curve to this using curve fitting in R. We were able to generate the demand equation that you see at the top of your screen there, starting in year count 1 at 1980. On that growth, you see the actual data in orange as it starts to grow, and you see the exponential growth of the projected data, which again, we're assuming is an exponential curve fit. And as you can see over the early part, comparing the actual and the projected data, it matches pretty well. This gives us something that allows us to project demand into the future, which in step 2 on the next slide allows us to project production based upon that demand. Now, while there's a very strong correlation in the raw data between production and demand, about 0.991 correlation between those two, there are slight variations between production and demand that varied anywhere from 0 to 10%. And again, these were relatively randomly distributed. There didn't seem to be like some function with time as to how much the two of them differed. So we randomly generated the difference between production and demand and used that to calculate a demand that was a certain percent difference away from each, calculate a production value that was a certain percentage change away from our projected demand values that we calculated in step 1. This allowed us to calculate a probabilistic projection of production. Now on that graph you see there, we ran 100 different iterations, extending it out 150 years after our data set. And there you can get an indication of the kind of variance that we saw just because of the probabilistic nature of it. This allows us to capture some of the uncertainty in trying to model or predict future behavior. On the next slide, we have to, in that difference equation, we have our depletion factor now. We have our change in production over time. But now we need to generate projections for new reserves, or at least find some way to predict it. Now our new reserves empirically, as we talked about, didn't really fit any kind of growth model. However, when we looked at the unique values in our empirical data set, the distribution was relatively normal. So what that allowed us to do is run a Monte Carlo simulation to choose the bin. We define the bins as you can see here. So a Monte Carlo simulation to generate a random number and choose a certain bin. And then the actual value out of that bin was chosen randomly with equal probability. And that was used as our value for each year. So this process was repeated for each year that we projected and generated a value for new reserves. Now we can combine all those together in a difference function, as we can see on the next slide. And what that allows us to do is project production and project new reserves within some probabilistic sense. So we projected 100 years out into the future, and we did that 1,000 times in octave. As you can see on the left, that graph on the left there shows each of the individual paths of how total reserves varied. And on the right, you see the distribution of how many years it took for total reserves to get to 0, which again is when natural reserves deplete. Since that is relatively normally distributed, we can calculate the expected value just by taking the mean. So for our base case, we got an expected value of 58.067 years until total reserves dip below 0. So in about 58 years, we would run out of resources. Now, we did this with the base model, but we also did this with some alternative solutions, which you'll see on the next slide, which just altered essentially just altered how we calculated production or how we calculated demand. We ran a model reducing the tax breaks given to producers of natural gas, which cut exports by about 7.8% and total demand by about 4%. That extended our sustainability from 57 to 62.908 years. Totally getting rid of exports as a way of decreasing the amount of production required. Increased our sustainability all the way to 76.538 years, and slowly phasing out natural gas electrical generation, which, as Nate said, is the biggest generator of electricity and is also the biggest use of natural gas. By slowly phasing that out for clean, renewable energy over a period of 12 years, we were able to extend our sustainability up to 101.78 years. And again, these were just derived from the same process we just talked about for the base model, just by changing the demand function given the constraints for each of them.
Okay, interpretation and refinement of these results. What are these results really telling us about the data we collected and about the problem we're trying to solve? Our results, based on comparison with the EIA, are quite similar. Now, there's some differences in the assumptions made by the EIA and their model and the assumptions we made in our model. The EIA assumed to use both unproven and proven reserves in their model. So if we remove unproven reserves from their model, and we also add the component of non-constant consumption levels as time goes on, so we assumed that consumption would increase as population increased, we see that the difference between their estimation of 90 years and our estimation of 58 years in our original base model, when we account for those things, the numbers seem to indicate that we moved closer towards their approximation, which is a good thing and gives us credibility when our results compare well with a national administration for energy consumption. So when confirming that, that kind of confirms our assumptions that also the eventual exhaustion of the resource. With our intuition, we predicted that a limited resources would eventually deplete so long as new resources or new discoveries couldn't outpace the consumption habits and the growth in population and GDP that we see and that we would expect going into the future. Now, our best option going forward, as you can see based on our model, supposes that a reduced use of natural gas as a source of electrical power in the United States would provide the biggest boost in terms of the longevity of natural gas as a use, natural gas in general. Now, is that entirely feasible in 12 years? Maybe not. You know, the sheer infrastructure required to transition that large portion of electrical generation within the economy is quite difficult. But when we think about the strengths and weaknesses of our model and how well we were able to predict those things compared with the EIA, we see that some of our strengths is that we were able to capture the unpredictability of the future using those random processes and the Monte Carlo simulations within the model. Also, we were able to account for growth in consumption as population and GDP grow. We didn't assume constant consumption, and we wouldn't expect constant consumption intuitively as we have more people consuming more resources. Weaknesses within the model, we don't account for the increases in prices due to scarcity. And economic understanding tells us that as prices increase, the behavior of both producers and consumers change, so that we would expect less consumption and less production in the future as these prices increase. Also, we assumed, another weakness is that we assume that future discoveries will be similar to the past. As we discover more and more resources, the opportunity to discover new resources becomes smaller, and we didn't account for that in our model. We assumed that we could still find similar results or similar discoveries as we had in the past, despite a depleting availability of those resources. Some opportunities to improve our model. One would be to fit population growth and the discovery of new reserves with logistic curves. we understand intuitively that population growth and new reserves can't grow exponentially forever. Eventually, due to carrying capacity of the planet or the availability of new reserves that exist on the planet, new reserves and population growth will have to taper off eventually. Also, we could incorporate a relationship between price and the actions of producers and consumers. Incorporating price within scarcity would help promote the longevity of the resources as people change their behavior due to the increases in price and scarcity of a very beneficial resource. And then lastly, modeling growth and consumption more meticulously and intricately, as Scott mentioned before, the demand function is a really complex piece or equation and has a lot of moving parts within it. We've really simplified our model, but if we really want to capture the growth in consumption, we really need to capture as each individual part grows at different rates would affect the consumption level overall of natural gas in the United States. As we look toward the future, as we look for alternative energy sources, clean energy sources, the limitations of renewable energy in terms of the physical limitations of those systems of converging hydroelectric, solar, wind power does not appear to be able to support the energy demands of the future. However, technology growth in nuclear energy does seem to be a promising future if we look for alternative sources of electricity. But with that said, that is the end of our presentation. Thank you for listening.